Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on January 29, 2026, about 5 days ago. It reports a surprising null effect, finding that reasoning models trained via reinforcement learning with verifiable rewards do not yield better semantic embeddings than standard base models. The paper is titled, "Do Reasoning Models Enhance Embedding Models?" And as we'll see later, the author's new analysis framework uncovers a phenomenon called manifold realignment that explains why this paradox exists. And for those interested in the implementation, the authors have shared their code on GitHub. You can find the 0.5 billion and 1.5 billion parameter models on Hugging Face, including Python code, to help you encode queries and calculate similarity between your documents. Figure 1 illustrates the core hypothesis about how different training methods affect the model's internal representation space, or latent manifold. At the top, we see the transition from a base model to a reasoning model, using either supervised fine-tuning or reinforcement learning with verifiable rewards. The crucial insight sits on the purple surface. The representations for the base model and the reinforcement learning model, labeled Z-base and ZRLVR, remain very close together. In contrast, the supervised fine-tuning point, ZSFT, jumps to a completely different location. When we apply contrastive learning, indicated by the vertical arrows, this relationship holds true, which explains why the final reasoning embeddings end up surprisingly similar to the base embeddings. Table 1 presents the concrete numbers backing up that hypothesis. It compares embedding performance across multilingual, code, and bright benchmarks. Notice the supervised fine-tuning row for the Qwen 3 model. There is a massive drop of over 12 points on the multilingual task, showing that fine-tuning can significantly harm semantic representations. In contrast, the reinforcement learning with verifiable rewards section below tells a different story. Across models like Qwen 2.5, the performance gaps in the delta columns remain near zero, confirming that this method essentially preserves the base model's embedding quality. So, to explain this performance parity, Figure 2 introduces the Hierarchical Representation Similarity Analysis Framework. This tool splits model comparison into 3 levels. The representation level, on the left, checks if the raw features line up on the exact same coordinate axes. In the middle, the geometry level focuses on the shape of the data cloud, ignoring simple rotations. Finally, on the right, the function level tests if a shared linear probe, essentially a simple readout layer, can extract the same answers from both models, proving they solve tasks in compatible ways. Table 2 summarizes the results from that analysis, revealing a stark contrast between training methods. If you look at the supervised fine-tuning column, the terms are severe: destructive mixing, anisotropic distortion, and degraded linear readout. This confirms that standard fine-tuning fundamentally restructures the space, often damaging the pre-trained geometry. However, the reinforcement learning column tells a different story. It shows preserved coordinates and isometric geometry, indicating that this method only optimizes the trajectory without breaking the underlying map. Finally, the post-contrastive learning column on the far right demonstrates manifold realignment, where the model successfully realigns the representations, effectively smoothing out the minor drifts introduced during training. Well, Figure 3 visualizes these structural differences directly using heat maps. The left block measures dimension-wise correlation, which checks if individual features match up one-to-one between the base and reasoning models. In the SFT column, the maps are faint and scattered, meaning the feature correspondence is largely destroyed. However, the RLVR column next to it shows a strong diagonal line, proving that the reasoning model keeps the same coordinate system as the base model. Moving to the right block for linear CKA, which measures global shape similarity, we see the same pattern. The SFT side is dark blue, indicating low similarity, while the RLVR side is bright yellow, showing that the global geometry remains nearly identical. Now, Figure 5 reveals the training dynamics behind this result. It tracks alignment metrics from the raw backbone at step 0 to the final model at step 781. In the top 3 panels covering correlation and global geometry, we see a rapid realignment phase, where the curves shoot up or remain high. The green arrows label this manifold realignment, showing that contrastive learning quickly forces the reasoning model's global structure to match the base model. Conversely, the bottom panel for KNN overlap stays low and flat. The red arrow here confirms that the local changes to the geometry are irreversible, meaning the fine-grained clustering remains distinct, even as the broader semantic map aligns. Wrapping up, 2 key takeaways stand out from this study. First, despite better reasoning capabilities, models trained via reinforcement learning with verifiable rewards do not outperform base models on embedding tasks. Second, the authors find that this training method acts as trajectory optimization. It refines how the model navigates existing knowledge, but it does not fundamentally restructure the global semantic map like supervised fine-tuning does. This suggests that the base model's pre-trained knowledge remains the primary driver of embedding quality. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.